to announce the talk of Professor Doi.
Okay, thank you. I start my talk and just thanking the organizing committees for inviting me to this conference. My talk is slightly off the main line of the theme discussed in this talk. I will talk about the dynamics first, and then it's not restricted to these liquid crystals, but I'm going to discuss the more general non-equilibrium phenomena, which that you see in the many soft matter systems. So I'll talk many things. I just start my lecture just saying my conclusion. The conclusion is this one. Okay, so first of all, soft matter. Soft matter is stands for a very large class of materials, including polymers, colloids, and surfactant, and liquid crystals. They all consist of some big units, and they are typically the dynamics is slow, much slower than the atomic systems. It is often called the complex fluid because it is something between the fluid and solid. And the liquid crystals, as you see, that it's something between the liquid and crystals. And polymers also is something between this very rubbery materials and this fluidic materials. So it shows a very complex responses when you stretch it, when you squeeze it. And it also has this characteristic of nonlinear response. It is soft, therefore by weak forces you can induce a very large deformation. You can induce a very large response by weak forces. These are the characteristics of soft matter. They are strongly nonlinear and non-equilibrium responses. And the conclusion, the message I want to say is that these phenomena can be discussed quite generally based on the Onsager's variational principle. And where you might wonder what's Onsager's principle. And so this is a principle that Lars Onsager presented in his a seminal paper in 1931 and 1931 in which he proposed this reciprocal relationship. And so it is a principle stated in that paper, but I think that is not very well documented. Many people have used that, but it is not on the surface of the usual literature. So the thing I want to show you is that this is a very useful tool that you can use in deriving equation and in getting some right, at least a proper set of equations. So this is the outline of my talk. So I first start my discussion with this variational principle in Stokesian hydrodynamics. This is a much more concrete system. And then I move on to the discussion on the main topics, Onsager's variational principle in general irreversible thermodynamics. What it is, and I discuss when it works, and then I discuss one useful formula. Then I I'll show you 3 applications that demonstrates the usefulness of this principle in the dynamics in colloidal solutions, in the dynamics of gels, and in dynamics of the liquid crystals. Then I summarize. So let me start with a very simple system, the variational principle in Stokesian hydrodynamics. I'm a bit ashamed. It's too simple, very simple. Let us consider the motion of a particle sitting in a fluid. The fluid sediment and the gravity, and you know that the velocity, the sedimentation velocity of this particle is determined by the balance of 2 forces. One is the gravitational force that is given by mg. This is derived from the potential of the particle. Now m, of course, stands for some correction, the renormalized and mass, and accounting for the buoyancy force. The other force is the frictional force. As the particle moves in a viscous medium, the fluid exerts a frictional force, resistance. And that it's known that this frictional force is proportional to the velocity r dot. R stands for the position of this particle. And the velocity, or the time evolution of the position is determined by the balance of these two forces. So that's frictional force and this one, the potential force are balanced. Now, this force balance equation can be put into a variational principle by very simple rewriting. We consider what I call the Leylerian. I always have some difficulty in pronouncing. So it is first term of R stands for is called the dissipation function, theta r dot square, and it represents that the dissipative energy per unit time when the particle moves with velocity r dot in a fluid. And the second term stands for this UR dUdr times r dot is the change of the potential energy when the particle moves with velocity r dot. So this is a quadratic function of the velocity, and this force balance equation is just the minimization. If you take a derivative of r with respect to r dot, then you have this equation. Okay? Very simple. So this principle is often called the principle of the least dissipation of energy, and that's maybe very old. Rayleigh first proposed this form of the dissipation function formalism. Now, that's a very trivial thing. Now, just imagine that. Let us now consider the motion of two particles sedimenting together simultaneously. Now we have two, the R1 and R2 the position of these two particles, and the force balance equation in this case is written in this form. Now, in this case, the force acting on this particle, the potential force is acting on this particle is still given by the partial derivative of the potential with respect to the position of R. Now, the frictional force is slightly different, because now if you have two particles moving in a fluid, the motion of this particle, number 2, particle 2, it induces a fluid flow. It induces a velocity within a fluid, and therefore it contributes to the frictional force acting on the particle 1. And this is called the hydrodynamic interaction. And therefore, if you use the Stokesian hydrodynamics, the low Reynolds number hydrodynamics, the Stokesian hydrodynamics, you can show that the frictional force is always written as a linear function of the velocity r1 dot and r2 dot, and then there's the coefficient theta11 and theta12. This is a function theta11 and theta12 are called the frictional coefficient. They are functions of r1 and r2. It depends on how far these particles are separated. Likewise, the second equation represents the force balance equation for the second particle. And the very important thing is that this frictional force is symmetric. This theta ij is equal to this theta ji, the transpose. This is actually the tensor. This reciprocal relation is known in hydrodynamics. It is known as a Helmholtz. Helmholtz. No. Liner, right? なんだっけIt's just slipped away. Lorentz, yeah, I think yeah, was if I remember correctly, yeah, it's called Lorentz reciprocal relationship that you can prove by starting from this, by starting from the Stokes chain equation, by solving the linear, the hydrodynamic equation, in the Stokes chain dynamics. The equation for the fluid velocity is written is a linear equation for that, and from that you can show this reciprocal relationship. And therefore, that this force balance equation is again written in this by constructing this Rayleighian. So you construct this energy dissipation function term plus the time derivative of the potentials, and just by minimizing this Rayleighian with respect to R1 dot gives this first equation, and then the R2 dot gives the second equation. Okay, so this okay. So now, of course, this argument can be generalized. In general, we have a very complex potato shape like particles, and so the configuration of the particle or the set of particles are represented by a set of the generalized coordinate. If you have f degrees of freedom, we have f parameters x1, x2, and xf. In the case of the if you have particles, there are some potato-shaped particles. It includes both the position and orientation. For the rigid body, you have each particle have 6 degrees of freedoms, and if you have 2 particles, the total number degrees of freedom of the system is 12. And if these are the generalized coordinate changes with velocity xi dot, the frictional force that is conjugate to the degrees of freedom of I is written as a linear function of this velocity xj dot. And this, again, by this Lorentz theorem, reciprocal. There is a Lorentz reciprocal theorem which says that theta ij is symmetric. Theta ij is equal to theta ji. And therefore, with this reciprocal relationship, you can rewrite this the force balance equation for x I dot in terms of this variational principle. Okay, so the dissipation function plus the term of u dot, and so the time evolution xi dot is determined by just minimizing this Rayleighian with respect to xi dot. So this is just what I am saying is just if you have a set of linear equations of this type, and if this coefficient is symmetric, then you can write this time evolution equation in terms of this variational principle. Right, now the reciprocal relation is, let me emphasize this point again, is not a trivial relationship. And it says, for example, that if the particle moves, or maybe if the particle moves with velocity v, the frictional force is not in general parallel to is not parallel to the velocity. It's different. The frictional force is not parallel to the direction of the velocity. If your particle is not the spherical, and so but then the reciprocal relationship. In this case, I am saying that maybe I'm applying a force in x direction, then the particle will move with a velocity v, which is in general not parallel to the applied force F. if we apply a force in y directions, then the rod will move with the velocity that is not parallel to the force Fy, in this direction. And the reciprocal relation says that Vy, the y component of the velocity in this situation divided by Fx is equal to Vx over Fy. This is well. This is not well. Okay, for some of you it may be trivial, but it's not an entirely trivial relationship. Likewise, if you have some helical particles, if you apply a force F, the rod starts to rotate with angular velocity omega. And similarly, if you apply a torque on this helical particles, the rod will start to move. Like if you rotate the screw, that the screw will start will move with velocity v. And in the Stokesian limit, low Reynolds number hydrodynamics limit, the omega and f is proportional, and there is this mobility coefficient. And in this case, v and t, the velocity induced by the torque is proportional to the torque. And the reciprocal relationship indicates that these two coefficients are equal to each other, and that's the result of the Lorentz reciprocal relationship. And again, this can be proven by hydrodynamics. Now, okay, let me emphasize just to make things clear. This is, of course, written in a textbook, for example, in the Lagrangian mechanics, in the Landau's textbook of the classical mechanics, Goldstein's book. It says that this is the Lagrangian is constructed by, so you have a generalized coordinate x1 to xf, and then you can construct the Lagrangian, which is the kinetic energy minus the potential energy. And this, if there is no dissipation function, that is this is the Euler equation that determines that you learn in classical mechanics. If there is if the system has a frictional force, like if these particles are moving in a fluid, then the Rayleigh proposed that we can take into account the effect of the frictional force by this formula, where phi is the quadratic form of the velocity, and theta ij is the friction constant. And what I'm talking about, what I am talking is that, in the situation, this inertia term is ignored. That this is essentially the force. This equation essentially represents the force balance equations, and it is this. It is what I'm saying is just what I am saying is the Lagrangian mechanics with frictional terms. Okay. So it's written in a textbook of classical mechanics. Now, okay. So now let me go on to the main topics. Onsager's variational principle in irreversible thermodynamics. This is actually the principle was stated in Onsager's paper in 1931, and he says that just imagine a non-equilibrium state where the state non-equilibrium state is specified by a set of parameters x1, x2, etc. So these are the slope variables describing non-equilibrium state. And if the entropy can be represented as a function of these slope variables, and Onsager says that in many kinetic equations, that we encounter. Many phenomenological equations are written in the form that the time evolution of these slow variables is proportional to the ds dxi. That is this essentially that's the thermodynamic driving force that brings the system, tends to bring the system to the state that entropy is maximum. And there is a coefficient, Lij. Now, what Onsager has done is that if you assume this kind of phenomenological equation is correct, then he proves that the coefficient L is in general symmetric with respect Lij is equal to Ljr. And this is this celebrated Onsager's reciprocal relations. And in the same paper, and he showed that accordingly, therefore, that the somehow I don't know, maybe. So if you consider this construct, this time evolution equation is written in this by precisely the same formula that I described previously. So precisely by the same formula for the particle, for the motional particles in a viscous fluid. The entropy change term and this the dissipation function term or entropy production term. Or let me go on to this. To simplify the argument, I will restrict my discussion to the isothermal system. The temperature is assumed to be constant. I consider that situation alone. Then everything is written in the same form as the equation of motion for particles in a viscous environment, fluid. So the time evolution equation for the slow variables, for the variables that describes the non-equilibrium state, is derived by minimizing this function. The first term, well, I still want to call it a dissipation function. If the temperature is constant, so this term stands for the dissipation function term, and this term stands for the change of the potential. Well, in this case, I wrote it A. The symbol A now stands for the free energy of the system. Free energy of the system. So the R is now written as the summation of the two terms against the same term. Phi is the dissipation function, energy dissipation function, and it stands for the work done to the dissipative system per unit time. Okay, the dissipative meaning. Okay, I come back to this. Maybe just imagine, just for me, and maybe it's easiest for you to understand what I'm saying is that the xi is still stands for some the Brownian particle, some particle coordinate, and the other variable, the dissipative system, or the other variable is the fluid, the system that consists of the fluid molecules alone. Okay. And so the A is the free energy of the system, and then now of course the time evolution equation, the phenomenological equation, plus the reciprocal relationship can be represented in this simple form. Now, okay, there are essentially two, maybe, okay, Onsager's proof for so the key to this principle, variational principle, is the reciprocal relationship. And Onsager essentially used this as the same argument that Einstein used in his Einstein's formula for the diffusion constant. essentially that he said that, okay, this is a very brief outline of his proof. He said that, so the xi is a slope variables, and let us assume, this is an assumption, assume that the the time evolution of x is written in this form. Now, it is very important to say that this evolution equation laws consists of two terms. One is this is some dynamic force, and this what I call the kinetic coefficient or the frictional constant term. Essentially stands for the effect of the first variables. Now we have the statistical mechanics generally deals a very large number of degrees of freedom, but we are considering now. Just imagine this case of the Brownian particles, Brownian motion, or the motion of big particles in a fluid. We pick up certain the position and orientation of the particles are slowly varying variables. It varies. Its time evolution of these variables vary much slower, much more slowly than the fluid variables, the first variables. And the kinetic coefficient term Lij reflects the effect of the first variables, and this is a driving force that is essentially determined by the interaction between the slow variables, and this term, the frictional term coefficient, is determined by the first variables. And the essential assumption here is that this equation is this term is unaffected, so is not affected. Suppose we just in okay. If now the important implicit assumption of Onsager's argument is that this form of time evolution equation is valid for any potential, for any form of the of this driving force term S. Put it in form of this, okay, just imagine this the fluid particle, the particle system in a fluid. Okay, so if these particles are moving and interacting with each other, they do a very complex system. The system is far from equilibrium of the whole system. But the we can make the system close the equilibrium by just applying an hypothetical external force on individual particles. We just pick up. We just apply a force that balances with the gravitational force. Okay, by imagining such hypothetical operations, we can imagine that the system is close to equilibrium. So the S can be the system can be close to equilibrium, and that part. So if we apply an external force, if we apply a hypothetical force, we are changing this thermodynamic driving force term, but we are not changing. This is an assumption is that this frictional term, kinetic term, is not affected by the by this hypothetical force. And he says that we can now assume that the system is close to equilibrium, and so we can assume that Sx has this quadratic term where xi now stands for the deviation from the equilibrium value of x. And then we can calculate the time correlation functions, and by using the same argument that Einstein used in deriving the fluctuations of the the Brownian particles. So you can calculate this time correlation function. And then Onsager says that in general, any fluctuations taking place at equilibrium, it has a time reversal symmetry. And therefore, that xi to xj0 is equal to xi. So it changes this is equal to the xi minus t, the time correlation function of the value of xi at time minus t, and xj, the value of xj at time 0. And so therefore it indicates. So this time reversal symmetry is a very general law of physics. And so therefore that he can, there is no mathematical, but you can prove that. So the assuming this time evolution equations, and then calculate, and then to calculate this fluctuation, you need to add up some random forces. But then you can calculate this quantity, and then the essential thing is that so the time, since the fluctuation taking place at equilibrium satisfies this time reversal symmetry, or this time correlation function is symmetric with respect to the exchange of I and j, you can prove that this Lij is symmetric. So the important thing is that this reciprocal relationship can be proven without invoking hydrodynamics. You can prove the general relationship. In a more formal way, you can prove the reciprocal relationship just by a straightforward perturbation calculation in statistical mechanics. Let me go back to this problem of this Brownian motion. So we have a big particles, and so then this blue particle stands for the particles of the fluid molecules. Now, the time evolution of the fluid molecules is determined by the Hamiltonian. Hamiltonian, that is a function of gamma. Gamma now stands for the phase space variables of the fluid molecules, and x is x is a position coordinate of the big particles. So we are considering the situation. We are considering the equilibrium state of fluid molecules at under a given position of big particles. Okay. So the x is now, I am now regarding x as an external parameters. So the external, it is an parameters controlled by external forces, and I'm just considering the motion of fluid molecules, the motion of first variables. If you take a derivative of Hamiltonian with respect to this external parameter, the control parameter, it stands for, this gives you the force acting on the Brownian on this big particles. And you can ask, suppose that, so you grab this particle and move it slowly with velocity xi dot, what will be the force acting on what is the force acting on this fluid particles? Then by a very straightforward perturbation calculations, you can prove that it is the average of the force acting on this particle is given by dA dxi. A is now the free energy of the system times the time that is proportional to the velocity of the particle xi dot. And this theta ij is represented can be written as the time correlation function of the fluctuating forces. And that is the fluctuating part of this force. So if the correlation time of the force is very short, so if this the time correlation of the first variables relax quite fast, you can replace this by a constant. You can ignore this time t. You can make this an integral from 0 to infinity, and since theta ij is written as a since theta ij is written as an the correlation function, it has due by the time reversal symmetry of the fluctuating thing, that the theta ij is symmetric. So anyway, so what I'm saying is that this Lorentz reciprocal relationship is not restricted to the hydrodynamics. It is a very general relationship, and that describes this nonlinear non-equilibrium. Like the ohmic law, you have some network system, and you have some applied voltage, and you can there is a relationship between the applied voltage and the current flowing across a circuit, and there is a similar kind of the reciprocal relationships that have some different names, but many other systems, many other reciprocal relationships are known, and they all come from this Onsager's reciprocal relationship. Let me just summarize when Onsager's principle is valid. I think we can write down this the Onsager's time evolution equation for the system that if we properly select a set of slow variables, and these slow variables has to be chosen in such a way that if this set of slow variables are given, the velocity or xi dot is determined uniquely determined. For example, if you have two particles and connected by spring, and if they are moving in a fluid, so the x1 and this two sets x1 and x2 are the slow variables in this system. You can't construct this Onsager's type equations just by selecting x2. If you forget x1, you have to choose a complete set of slow variables. Or if you take into account what are the slow variables is precisely the key main issue, or the key point of this argument. If you are taking into account of the effect of Brownian motion, the current state is described. The non-equilibrium state is described by the distribution function of x1 and x2, psi x1 and x2. That is the slow variables. And your task is to determine this term evolution of these distribution functions. And so first, you need to select the complete set of slow variables. And the second thing is that first variables are close to equilibrium. The fluid molecules they are not far from equilibrium. They must be close to the equilibrium. Close enough so that this frictional force is proportional to the velocity of the slow variables. Okay, now a brief thing that is again a very simple thing. That now what I have said is that indicates the following formula. Now, let us consider that the single particles sedimenting with in a fluid. Now we ask the question that so the now okay so the if we just imagine that we apply certain force to the system and move the velocity of the particle. We move the particle at a controlled rate x dot. And what is the force we need to apply to move this particle with velocity x dot? And the answer is obviously this thing, this frictional force plus this gravity. And this is precisely given by this the derivative of radian with respect to this x dot. Okay, it's a very simple study. And the generalization of this argument, you can prove that if your radian includes a set of external parameters, the parameters that you can control externally, the force that is needed to change the external parameters are given. You can now the radian in general consists of two terms, consists of two variables, includes two variables. One is the slope variables that describes the non-equilibrium state. The other is the the external parameters that you can control externally. And if you write down the radian, the partial derivative of radian with respect to this the time L dot. L now stands for the external parameters. Stand for the force needed to change the external parameter at the rate L dot. Several applications that for example, that this is a simple situation that you confine a particle with some semi-permeable membranes, and you push this semi-permeable membrane with some rate. So then you ask, so if you push this semi-permeable membrane with rate L dot, what is the force that is needed? And that is given by this formula. Likewise, if you have a gel, and if you apply, so you squeeze it. You squeeze the gel, and you change the distance between these. You have some. This is a gel, and you change the thickness of the gel H with H dot. What is the force? And the force is given by this formula, just a partial derivative of radian with respect to the external parameters. If you have some solutions, be it rod-like molecules or some colloidal solutions or the polymer solutions, you can write down. You may be able to. If you can write down the radian, and then the radian includes the position of the. Okay, so this solution is now confined in a box where the top plate is moving with the velocity x dot. X is this distance, the shearing distance. Then the force that you need to move the top plate is given by this formula. And by generalizing this formula, if you write down, if your radian involves the velocity gradient tensor kappa alpha beta, this is the stress tensor of the system is simply determined by this partial derivative of the radian with respect to the velocity gradient tensor. This is a very general statement and useful statement. Okay, sorry, I'm using up my time. So let me quickly move into this some applications. From now on, I'm going to very quick, and but I'm just repeating the same kind of argument. This is the first problem of the sedimentation of colloidal particles. Okay, the colloidal particles are sedimenting as the concentrated solutions of a set of colloidal particles. Now we want to write down now the slope. What is the stoic variable? And we want to describe this non-equilibrium state in terms of the concentration, where phi stands for the, in this case, I call it the volume fraction, but concentration, okay? Concentration variables. Concentration of colloidal particles at position r and at time t. And I want to derive a time evolution equation for phi for the concentration. And so to derive that, I want to write down the Rayleighian that involves the energy dissipation function and the time derivative of the potential, the free energy, let's say. Now, to write down the energy dissipation function, I think it's easier. I think what it is because phi, the change of phi has to satisfy this conservation equations. Phi, so there must be some velocity dp. So we can, instead of writing the energy dissipation function using phi dot, it is convenient to write down the dissipation function using this average velocity of the particle Vp. Okay, so this is the advantage of the variation principle. You can choose any variables, just to find the minimum state. Now then, so the dissipation function of, I think you can is written as a quadratic form of the particle velocity times coefficient. Coefficient may depend on the concentration of particles, but this is the dissipation function. And the free energy of the system is again written. The first term stands for the free energy density of these particles that involves the interaction between the particles, and then the gravitational energy. So the rest of it is a very straightforward calculation. A is given by those. Therefore, A dot is given by just A dot is phi dot times this one and this, and by using this conservation equation, you can essentially write the A dot term as a linear function of the particle velocity with some coefficients. So this is the expression for the then you have some. Then you have some here the effect of the free energy term. It can be written in terms of the osmotic pressure. Then then you have this Rayleighian form, and from the variational principle, by taking by minimizing this with respect to dp. dp is determined by this one, and this plus the conservation equation determines the time evolution of the particle, the sedimentation of the colloidal particles or in a concentrated solutions. Now, of course, now in the previous argument that I assumed that this fluid is at rest. This is not always the case. If you have an colloidal particles and if they sediment, you see that the whirling, the velocity, the fluid velocity also is also induced within the sample. And so this actually that the sedimentation generally, or in general, the diffusion generally induces the macroscopic velocity of the fluid. And so we have to, in general, we have to couple the velocity dt polymer, or maybe better to call it the particle velocity dt. This is the velocity of the particles, and this is the velocity of the solvent. Okay, so this is the volume average velocity of the fluid, or we call it the material velocity. And then the coupling can be described by now, if the material is moving with velocity v, and the energy dissipation consists of two terms. One is the motion of the particles relative to the materials. That this first term stands for the effect of the particle motion relative to the background, and the second term eta phi is the second term comes from the viscosity of the fluid. Then the rest is the same. So by just repeating the same set of the calculation, you have this you have a set of equations that describes the particle velocity and this the velocity of fluid induced by the sedimentations. And I'm not going to detail. Precisely the same kind of argument can be used for the gel dynamics. In a gel, so this Zoll, here the we have a particles and moving in a fluid, and this is a situation that we discussed in the previous slide. And if this the background, this particle from a network, we have a gel, and then I think the time evolution equation it can be in the slow variables here is a concentration profile. And slow variable in a gel is some displacement vector of this individual network, polymer network. And the velocity of the particles, the velocity of the gel network are determined by the Onsager's variation principle. Just by straightforward calculation, you assume free energy in a Zoll state is written as a functional of the state as the concentration, but the free energy of a gel in general is involves this gradient of the displacement. And then the rest is straightforward. Okay, I skip that part. Okay, and finally, so the since this is Ericsson Leslie stuff. So now let us now consider this and how to apply this principle to this to derive the time evolution of this liquid crystal nematic liquid crystal system. Now slow variables here is director nRT. Given n, you have so the free energy is determined. The free energy in this case is determined by the Frank energy in the simplest case, and then you ask that what is the energy dissipation when the director changes with rate n dot? But bear in mind that in this case that the n is also affected by this convection of the particles. The director field is also affected by the convection of the fluid. So we need to, in describing the time evolution of n, we need to introduce this velocity of the fluid. You construct this energy dissipation function, which is again this energy dissipation function term and this a dot term, and well, these comes from the constraint that director is a unit vector and the velocity is the fluid is incompressible. The precise form of the dissipation functions, here you can determine just by using the symmetry argument and this framing difference. And then you can show that this energy, so this is the set of equations that displays that the energy dissipation function is a quadratic form anyway with respect to the velocity and n dot. And these complex form are needed in order to ensure the frame indifference of the energy dissipation function. A is written as a function of this Frank energy, and just by repeating the procedure, you get the Ericsson-Leslie's equations for n and v, and of course that the Parody's equation that of course comes from the reciprocal relationship are automatically guaranteed in the time evolution equation. If you go to the more detailed description of the system, you can describe the current state of the nematic liquid crystals just by using the distribution function phi ut. And then you derive the time evolution of phi in terms of time evolution using the Onsager's principle. This first term stands for this conservation equation, where the omega is the angular velocity of the rod. This equation stands for the conservation equation. And so you can write down the energy dissipation function, and this is what you have seen the expression for the free energy of the system as a functional of psi. You have seen this formula many times in this conference. Then just no, I do not repeat just by the straightforward calculation, you have this time evolution equation for phi, and you also have this expression for the stress tensor. And this is the stress tensor that Professor Forrest talked this morning. And it describes some tumbling, kayaking, very complex, nonlinear phenomena. So I'm using up my time, sorry. So the conclusion is that many kinetic equations in soft matter dynamics can be derived conveniently from Onsager's variational principle. And the equation, the example I showed is diffusion, sedimentation, gel dynamics, liquid crystallines. And the variation principle, I think it's quite simple and easy to use. So that's what I want to say. So that's maybe on the kinetic equation that involves for Q tensor formalism, and the kinetic equations, the dynamic equation for the synaptics. Maybe, well, of course, this has been derived. I know that. So maybe I think you will get. I hope. I suppose. You'll get the same equation out of this Onsager's variation principle in a compact way. Thank you very much for your attention.
Thank you very much for your talk. So we have time for several questions. So,
I'm confused about how to understand the variational principle when the friction coefficients depend on the state variables, right? So, for example, in your sedimentation problem, can you go back to the slide, the first slide for the sedimentation problem, right?
Maybe, okay, yeah. This one.
Well,
maybe. This is
this, and okay, let's just stay there. Fine. Okay, so suppose the friction coefficient, the zeta, depends on position. Right. If we want to minimize the Rayleighian, right? To minimize it, we can't just be differentiating with respect to R dot. We must think about the dependence on R also, right? I mean, why isn't there any differentiation with respect to R in there?
This is what Rayleigh said, that we should do this. Okay? Just introduce this the dissipation function and just take a derivative of the dissipation function with respect regarding the velocity as an independent variable.
Well, okay, but I mean, it's when we talk about minimizing the action to derive Lagrangian dynamics, right? Then we have an equation that involves derivatives with respect to x and x dot, right? But here we don't. Here we only have.
Okay, this is Rayleigh. This is Rayleigh's prescription. Let's call it.
Well, okay, but here you have an up-to-date version, right? But it's still a variational principle. So something is being minimized, right? Or does this variational principle not go to a minimum? I mean,
well, it is minimum with respect. But this is usually the quadratic form for the velocity.
Yeah.
So the taking the R dot. The minimum state for the velocity with respect to the velocity.
Okay. Well, let me. So here's a particular problem that I'm concerned about, right? So with the application to liquid crystal dynamics, okay, and so you have this nice derivation of Leslie-Erickson, right? So one of the many things you could calculate from that is shear alignment of a liquid crystal, right? That if you put on a shear, then the liquid crystal will pick some orientation of the director, right, with respect to the shear, right? So if we think of this as a variational principle, right, then we should be able to say there's some amount of energy dissipation when the director is at this orientation compared to some other orientation, right? And this is the best orientation
I
that
want
way.
to answer to that question. Okay, so it's now, okay, formally, no, this does not say that this variational principle does not predict the steady state. It only predicts the time evolution equations. So basically what you have to do is, okay, I'm not saying anything new. What you have to do is just to derive the time evolution equation for the n, and then find out the steady state solutions. Now there is a possibility that this steady state solution can be obtained by some sort of this minimization principle, but this is not directly stated in the principle that I.
Well, okay, but it's just a little bit misleading to call it a principle of least dissipation of energy, or I mean, maybe I'm blaming Rayleigh, right? But it was misleading for him back then to call it a principle of least dissipation of energy. It should be like a principle of here's a good way to derive dynamic equations by calculating some derivative.
Okay, I think this discussion can be continued later on, but we have two more questions who have been first. Tom, please.
I was going to ask a similar one, but in that same vein, when you look at the Onsager, at the Kubo relations, so we're used to doing those force correlation functions when the dissipative coefficient does not depend upon position.
No, sorry.
So suppose zeta depends on r, and you calculate it using the Kubo formula.
No. Okay, no. This is a situation.
There we go. Yeah. So that the f's depend on x there.
Yeah, that's right. Yeah.
And you just keep x fixed and do the calculation.
That's right.
For whatever else.
To calculate the x-dependent coefficient, so you fix two particles here and just measure the force, fluctuating force acting on the individual particles.
I see. So you fix it, and the same thing as if you have a wall, you fix the
Yes,
particle.
that's right.
I see, and that works.
Yeah. Yes, it works.
So I want to make a couple of comments. So when Onsager put this paper together, he actually made a note that it was a maximum entropy reduction principle. And out of honor of Rayleigh, he basically redesignated it and wrote that less than physical combination of the sum. So that was a deference to Rayleigh, but actually it's a maximum entropy production principle, which mathematically is a gradient flow. So the benefit of viewing it this way, this is just basically a physics version of gradient flow, is that you're encoding the geometry of the flow. So in that sense, it plays the role of the dissipative equivalent of Lagrangian mechanics, which is again a geometric view of mechanics. And the sort of second point is that not only does it help you write the equations as you've shown, it's efficient at deriving the equations of motion, but it's also susceptible to asymptotic expansion. Because in the same spirit as Hamiltonian mechanics is a structure preserving thing, if you look at limiting dynamics, you want to preserve the structure. Similarly, when you look at defect dynamics, you've got a gradient flow, say for pneumatic, and a resulting evolving texture. The dynamics of that texture would respect this maximum dissipation principle in the sense that that's the structure that you should be looking for in the limit. So, it's a philosophical remark.
Maybe I may not be understanding you correctly, but so this defect dynamics, you can regard this configuration of the defect as a slope variables. You can calculate the dissipation functions. And you can derive the time evolution of the equation for this and deformation of the defect line by the same principle, right? By this principle, I believe.
See, maybe I can make a small comment, because indeed, since the times of Onsager, this has been a little bit developed, and so now this is known indeed as a principle of minimum entropy production. Not maximum. Yeah. And well, but never mind. I mean, what is important that the proofs exist for linear deviation from the equilibrium, and this answers part of the questions. So, for example, if there are cases when they depend on position, for example, I mean these coefficients, but position is not a thermodynamic variable. But if the coefficients depend on a thermodynamic variable, like the order parameter, for example, and it is time dependent, then we are outside the realm of linear irreversible thermodynamics. And in this case, variation principle is not valid generally.
I want to.
So we need to only consider linear deviation, and these coefficients depend on equilibrium order, and this is perfectly fine.
Let me just
Yes,
emphasize.
please.
Okay, so this for this segmentation of two particles problems, this is a very nonlinear, highly nonlinear equation for the position vectors, and this is far from equilibrium. The principle is still works. And this is the important thing is that so the slope variable may be far from equilibrium. The first, as long as the first variables are close to equilibrium, this principle works. So this is a point that is often not clearly stated in the books. It is for this Onsager principle to hold, the first variable has to be close to equilibrium, but the slope variable can be far from equilibrium. And this is why we can discuss this nonlinear viscoelasticity of liquid crystals, nonlinear viscoelasticity. We can discuss this nonlinear viscosity of the Ericsson density, the pneumatic hydrodynamics out of the Ericsson density. They are all linear equations, but the result can be, and the equation for the director is highly nonlinear, and therefore we can derive nonlinear response. We can describe the nonlinear response out of this out of this equation. Maybe we should discuss more.
Thank you very much again.